All right, well, it's 5:32. I'm going to get started. So I got an interesting email from apparently a student from one of the community colleges around Livermore. So I'm not sure how many of you read the announcement that I just sent to the whole class. So apparently someone from, which campus is that? Las Positas College in Livermore. They're planning to get a community codes, that's how they call it, a hackathon. It's going to happen in October 11th, 2019. So it's going to be in the fall semester. And they're calling for people to kind of give them ideas, or if anyone has experience organizing something like this, I guess they want to kind of get some help, organizing the whole thing, or at least get an idea of what needs to happen, what needs to be arranged, that sort of stuff. So at the end of the message, that was sent to me, there's a link here to a form of some kind. I haven't clicked it yet, so I have no idea what it is about. So if anyone is interested, you can go ahead and fill in the form and answer some of the questions. So it's definitely optional. If you guys are, feel like doing it, that's good. If not, just kind of ignore that. So are we good with this one? Okay. Yeah, so this one, I think the interesting part of this one is kind of like, it's kind of like our, the Sac City's ACM's Codathon, because this one is only for community colleges, so it's not including UCs and CSUs. So they only want to do it for community colleges. So maybe interesting to you, may not be interesting to you. It's up to you guys to kind of decide what to do with this. So with this out of the way, then we go to the other announcement. So the other announcement, I am hoping is a little bit more relevant or related to this class, because I'm giving you the C code that actually runs, that corresponds to your homework assignment that's due next Tuesday. So this is what we'll do today, is kind of have a focus on this particular program, and then we can kind of look into how the nodes are initialized in assembly code, and how the structure is done in assembly code, and also how the traverse program or subroutine is supposed to work. So do we have any questions about this sample program? How many people got a chance to open it before now? Okay. Was it helpful? Did you guys take a look at it and be able to relate what this program is trying to demonstrate to the homework assignment? Okay. More or less, sort of. Okay. All right. So the first thing we want to do is to really just to copy and paste it and run it. Okay, so we want to see how it runs and how to test this particular program, because what you're going to do is similar to what this program needs to do. So I'm going to make this program in my temp folder. I'll call this tree.c, and then we just paste, oops, there we go, and then gcc, okay, I need my glasses. All right, so we have gcc-o tree.c, compiles without a problem, and then we use gdb to find out how it gets the job done. Oh, okay, I forgot to compile with a -g that includes the debug information. There we go. So now we can actually list the program, and we can put a breakpoint in, put one in main and put one in traverse. Okay. Nope. Okay. Okay, maybe I just did not name. Oh, I misspelled it. Traverse. There we go. Okay. So the first thing we want to do is to look at the structures. Okay. The initialization of the structure, you can see it on the screen right now. N1, which is a struct node, has 3 members. So the first member is just a value, it's an integer. So in this case, I give it a value of 5. Okay. The other 2 are pointers or addresses of other struct nodes. So for the second one, which is, cannot remember, left, okay? For the left one, I let it point to node 2. So I'm taking the address of N2 and put it here. And then for the right one, I take the address of N3 and then put it over here. So are we doing okay so far with the initialization of the node structures? Yes?
So mm-hmm. Access because of the pointer to N2 and N3?
Say that one more time.
Okay, the N1 node N1.
Uh-huh.
Address, the address, two addresses to the other nodes. So node 1 has access to those node 2 and node 3?
Yes, so member L of N1 is the address of N2. Member R of N1 is the address of N3. Is that okay? So, and the other nodes are defined similarly. Yes? Yes, I believe so. Let's double check, let's see. Yep, we're recording and streaming, and the audio is good. So you're good. Thank you. All right, so that's how N1 is done, and then N2 is kind of like the same, except the value is 3, but we don't have anything to point to as far as member L is concerned. So 0 is the same thing as null, N-U-L-L, all uppercase N-U-L-L is really just 0, okay? So instead of using null, I use 0 here, because I can also use 0 in the assembly code. On the other hand, member R of N2 points to N4, and then N3 has the L pointing to N5, which is here, but the R member is null, is not pointing anywhere. And then N4 only has a value. Both L and R are null. And then N5 only has a value of 9. And both members, L and R, are also null, which means there's no one to point to. Is that okay? So as far as the C code is concerned, are we doing okay so far with understanding, how the nodes are initialized? Is that okay? All right. So what I want to do also is to display the assembly code side by side. The assembly code is in your homework assignment. So if you go to your homework assignment, you will see the assembly code for the initialization of the nodes. So let me get to that part first. And I'll do a preview, would do just fine. Okay, so there we go. And let me see if I can display both at the same time. Yeah, it's good. All right. So are we seeing a resemblance between, the C code and the assembly code? They're doing exactly the same thing. It's just that the syntax is different. Are we doing okay so far with this? Because I think some people might initially have a question of, what is byte N2? N2 is a label here, so what is byte N2 doing? Well, what it's doing is it's taking the value of the label N2, which is the address of this byte 3 here, and put that value over here. So it becomes the second byte of where N1 is located. Is that okay? So the other way to look at this code and to understand the assembly version of it is actually just to do it, okay? Put it into the assembler, assemble it, and then find out exactly what are the values corresponding to this byte, this byte, this byte, and you will see that they become the addresses. So this becomes the address of this byte, this becomes the address of this byte, this becomes the address of this byte, and this becomes the address of that byte, which is doing exactly the same thing as what the C code is doing. And by the way, there's no difference between the C code and the assembly code in terms of how the nodes are structured. So when you run your program using the nodes that are already initialized here, you should get the same result. Are we okay so far? Are there any questions? Yes, go ahead.
Okay, so you said
Mm-hmm.
byte N2 point, it has the address of the first byte of N2, right?
In the assembly code or in the
Yes,
C code?
assembly code.
In the assembly code. So in the assembly code, what this is saying is the first, so N1 itself is the label of byte 5. So that byte with initialized to 5 is, the address of that byte is represented by the symbolic name of N1. That's basically what N1 is. Okay, the next byte, which is this N2 here, we are reserving a byte and we want to initialize that byte to be N2. But N2 is a label, which means whatever it is, it's defined later. But you can see how N2 is defined. N2 is defined to be the address of this particular byte 3.
Right. Is that the only address byte 3?
Okay.
Can you access also byte 0 and byte N4?
Okay, how about this? We take this copy, and then let me find my assembler. Where's my assembler? Nope. I might have closed the assembler, so I'll just go ahead and go to my Google Drive again. And we'll just assemble that part. So we go to 310, go to shared, and then processor. And then go to assemble with postfix expressions. So this will only work with the assembler with postfix expressions. The other one would not work in this case. All right, it's loaded. Go to the source tab and erase everything in column A. And then just paste all this code here. Now I'm going to do something here to take up a few bytes initially. So this way, none of the structure starts at location 0. I just want to make sure that it doesn't start over there. And then paste the rest here. Okay. So the assembler has done its work already. And what we want to do is to go to the Assemble tab. This is the Assemble tab. And the Assemble tab is really helpful in many ways, particularly if you take a look at column W and column Y. Okay, so let's focus on just those two columns. And I can't scroll this any further, so this is kind of the best I can do in terms of lining up everything. So column W are locations. So this is at location address 00, address 01, address 02, and this is the content at that address 00000. But that's expected because no op has an binary representation of all zeros. So we kind of know that one. So when we get to N1, N1 itself is just a label. All it is just a symbolic name, but it's defined to be 3 because of the way we use the label definition. It is a symbolic name of whatever the location is at that point, and that is location 3. Because location 2 is already used, so the next available location is location 3. Is that okay? Then the byte 5 is just, it's just 5. Okay, there's nothing particularly mysterious about byte 5. The next one is byte N2. That particular byte is at location 4. But what is the content of that byte? According to this, the assembler knows that it is supposed to be 6. So at location 4, it has a content of 6. Why? Well, if you look at N2 itself is at location 6. So that is how it works out. Is that okay?
Yeah.
Cool. And it works out the same way, in the C code as well. So when you look at the C code, it really is the same thing because, this is the address of N2 and this is where N2 is. So what I use the labels for in the assembly code is to emulate, the effect of having these global variables in a C program. So are we good so far? All right, good, okay. So now we kind of focus on the C program and ask, okay, what is the C program going to do? So we run the C program, and of course, we have a breakpoint in the main program. So the first thing it does is to initialize P as a pointer. P is a pointer. P is not a really, it's not a pointer to a structure. It's a pointer to an integer. And it is initialized to point to the beginning of an array. X is an array of like 5 elements, okay? So P is really just pointing to the beginning of X to say that, okay, what is the first location for me to overwrite in the array? That's what P is doing. Single step. Then we have the recursive call to traverse. So what traverse, the first invocation of traverse gets would be the address of N1. That is a pointer to a structure. It will also have the address of P. That is why the prototype has star star, because P itself is a pointer already, but I'm taking the address of a pointer. So whatever I'm passing to traverse is a pointer to an integer. That's why you see star star uint 8 underscore t. Are we good so far? All right. So we can do some printing here. Okay, we can print x. X is an array, of a few elements, and it's currently uninitialized. Okay, so whatever it has, it doesn't really matter. But once we initialize p, it's the same thing. Okay, now it doesn't really show you that, but if you look at the address of x, it is the same as what p is initialized to. They both end with E16B because that's how we did the initialization. Okay, so we single step, and now we're getting into the first level of recursion. So you can see that GDB is pretty nice because it tells you what the pointer is, and it also tells you what the array is. Now, because we know that this address is corresponding to the base or the address of a global variable N1, it even tells you that, oh, that is really just the address of N1. So it's actually very nice. I mean, it tells you what it is. So when we get into the subroutine, the first thing we do is we check whether the pointer is null or not. And you can definitely tell the pointer is non-null. It has a whole bunch of 5s and then 80B0. So we're going to get into the subroutine. It wants to check whether the L member of the structure pointed to by PTR is null or not. Okay. Now, if you want to, you can actually just print it like this, and you can see that L as a member is non-null. Okay. So that means we have to go into that conditional statement. So once we get into the conditional statement, guess what? We have our first recursive call. Okay. But what we are passing is kind of interesting. We are not doing a single thing about array. Array is just passed along the way, the same way that I did, the original way. But the pointer is not passed as pointer. We are passing the L member of the structure pointed to by PTR. Is that okay? So this is the first recursive call. So when we single step into it, now we have the second invocation of traverse. The first one is not done yet. It is on the stack, but it is quote unquote not active at this point. So this is the second invocation. The second invocation, as the first one, it shows us that the PTR is a pointer to a structure, and in fact it is pointing to N2 as our global variable. Is that okay? Then we single step again. Okay, PTR is non-null, and now we want to see if the L member is null or not. And you can see that L is actually null in this case. So it won't do the first recursive call, and instead it will jump to this location here. And this is a little bit mysterious, right? So I did a little bit of explanation of what this means in the lab on Tuesday. So for people who missed the lab entirely, I'll give you a clue, okay? So I'm not going to keep it a big secret, but at the same time, I'm not going to spend too much time to explain that either. Okay, that's enough space, I think. All right. So star, and then we have another star array, and then plus plus inside the parentheses equals to what it was, I think it's PTR dash points to V. This really is the same thing as star star array equals to PTR points to V, and then followed by a plus plus of whatever array points to. Okay, so this line 1 is the same thing as line 3 and 4 combined in that particular order. Is that okay? All right? So this might help, if you are not really remembering your C code very much and you're not quite deciphering what line 1 is doing. I'm telling you, it's doing the same thing as line 3 and 4. Are we doing okay so far with this? So what it's doing is it is dereferencing array twice and then store the value that the structure, member V of the structure pointed to by PTR, that value is now stored to whatever is pointed to by whatever is pointed to by array. Well, remind me again, what did I pass as array from main? Ampersand P, right? What is ampersand P? It's the address of a pointer. How did I initialize the pointer? I sure hope so. Do you guys remember how I initialized the pointer? To the address of the array X, right? So that means array itself is the address of P in main, right? One dereference will get me local variable P of main, which is a pointer. But that pointer is initialized to the beginning of array X in main. So one more dereference means I get to the first element of X in main. So I'm going to store this value into the first element of array X in main. That's the end result of doing this. Is that okay? Are we still doing okay? Now, the nice thing about having the lecture recorded is we are at about 54 right now, like 20-something minutes from the beginning of the lecture. You can listen to it again, and even slow it down, and then listen to it again, and then listen to it again, and then draw a picture. It really helps to draw a picture, okay? Line 4, what is line 4 doing? Line 4 is doing some increment, but what is it incrementing? Okay, that's the big question. It's not incrementing the parameter itself. The parameter is nothing more than the address of local variable P of main. It makes no sense to increment it, okay? It is incrementing whatever array the reference to. Array is the address of P in main, so that means it is incrementing P, local variable P of main, which is a pointer into an array, okay? So it kind of makes sense to increment a pointer into an array so that I will be ready to overwrite the next available location of the array. Is that okay? So that is the explanation of these two lines of code, which in C and C++ and most other C-based programming languages can be combined into one single line to make it really cryptic. That was actually intentional. Because after taking cisp310, you really should know what the first line is, what is the meaning of the first line. So, but if you don't, that's okay. I'm going to give you line 3 and 4, which is equivalent, the equivalent operations. So are we doing okay so far with this code? Okay. So we get back into the debugger. We single step, okay? So remember what I said. I said whatever the value of the structure that PTR is pointing to is now the first element of the array X in main. Remember that's what I said? So the question is, well, how do we check that? Okay, I'll show you exactly how to check that. This is not exactly related to this class because we are using a higher level language feature, but you might find this technique useful if you have not taken 430 yet. You might find this technique to be useful in that class because if you have any type of especially recursive subroutines, this technique can come in very handy. So the first thing I do is I say backtrace, BT. And what backtrace does is it shows you the call sequence, okay? How did we get here? we got called from main on line 38 to the first invocation of traverse. That first invocation of traverse, okay, you can't see the rest. Let me move the window back. That first invocation of traverse on line 22 is doing a recursive call, and that's how we ended up in the second invocation of traverse, which is where we are now currently at on line 25. Is that okay? So it's giving you a full history of how we got here. Now, since I claim that this array is modifying a local variable in main, I should be able to check that, right? But if I say print x, it's not going to work because x is out of scope. It's a local variable. I'm currently in traverse. There's no x in traverse, okay? So what you want to do here is to use a command called frame. Frame followed by a number allows you to change the frame of the debugger from the current frame, which is where the execution point is, to an earlier frame. Okay? So the number that you want to put in is exactly the number of, after the pound, on each line of backtrace. So if I want to go back to the context of main, I just say frame 2. Now we're back to the context of main. And then we can now take a look at x. So x as an array, because it's an array of characters, so GDB is trying to be really smart about this, and it's printing it as a string. Okay? It's telling me that the first element of x is a 3. Does that make sense? Did we just put a 3 into whatever array points to? Maybe. Well, let's check again. So what we need to do now is to go back to frame 0, which is in traverse, and we want to know what is PTR pointing to. Well, PTR is pointing to N4 in this case, and the value is 3 indeed. So now we can correlate, what the recursive call is doing to things that we have set up earlier in main. Is that okay? So this is, if you step through this code in a debugger, like really line by line, step by step, and examine the parameters and understand what is really going on, that will help you debug the assembly code that you are going to write. Because unless you know what the C code is supposed to do, you cannot say whether your assembly code is doing something exactly the same or not. So that's the main purpose of the C code, is for you to have a reference of what your code is supposed to behave. Is that okay? Are we doing okay so far? Does everybody understand how to utilize the C code that I gave you to help debug your code that is going to be written in assembly? We good? Okay. So if we single step, then we are now going through another recursion to the right-hand side. So this is the last recursion. It's there are 3 invocations of traverse at this point. So BT can illustrate it, right? Because this is really kind of, well, to me this is visual. I know to you guys, who grew up in the media age, this is not exactly visual. But since I grew up in the command line era, this is actually very visual. Okay, you guys are not quite getting it, because you really have no idea of what is not visual anymore. But this is visual, okay? We start off in main. This is the first call to traverse. The first call of traverse calls traverse again recursively. That also calls traverse once again recursively, so that we are now here. Is that okay? Okay, so let's single step a few times. Again, so we single step. The L member is null in this case, so it's not going to do any further recursion. So it's skipping to this line here. So once again, we're doing something like this, okay? The first thing it's going to do is to take whatever value of the structure pointed to PTR is, and then store that to whatever is pointed to by the pointer that is pointed to by array. okay? And remember, array really is the address of P. Are you guys buying that? That array as a parameter is really the address of local variable P of main? Well, you should not trust me. So if you don't trust me and you say, I will believe it if I see it, how do you check that? How do you validate it? How do you verify this? Using the tools that we have just talked about, how do you check and say that, okay, array should be the address of local variable P of main. But how do you check that? How about something like this? You print array out, okay, which is my parameter of the subroutine traverse, okay, blah, 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 okay. Now, I actually remember this number, but let's just say that we did not remember this number at all, okay. Then we do a BT again, and we say frame 3 to go back to main, because now we are back to the context of main. Then we can say, oh, tell me, what is the address of P? Oh, it's the same thing. So now we know that array is nothing more than the address of P. Is that okay? But what is P pointing to? Well, P is pointing to that location. And exactly where is that location? How does it relate to X, right? So we want to look at the address of X, and we look at what P is pointing to. How do they relate? They're off by 1, because that 1 byte was used to store 3. And P got advanced to point to the next location. Is that okay? So that's how this whole thing works, is array is just a pointer that I keep passing around because it is the address of a pointer. If I want to advance the pointer, I now have a mechanism to change that. Is that okay? So I'm hoping that this is helping you to kind of understand the C code itself, so that you can now utilize what you understand about the C code to help you understand what your assembly code is supposed to do. Okay? All right, so I'm going to get out of the debugger because you guys can single step through this thing by yourself. Because this program is written entirely in plain C, there's nothing special about it. So you can use code blocks to debug it, like single step through the whole thing. Or if you prefer to do it like this, you can also use the command line version of GDB to do it. It's up to you, okay? I'm giving you all the tools to kind of trace through the program. But this is not going to help you too much unless you have main in assembly code, because I did not give you main in the quiz. So now, I'm going to give you this kind of help here. I'm giving you main that is equivalent to the main in the C code. So that way, when you write your assembly code, you can now actually test to see whether it works or not. Okay? So we'll see. Let me see. Should I use VI or should I use mousepad? Okay, your call. Which one do you like? Mousepad? Okay, fine. All right, so we are opening tree.c on one side. Look, it has in syntax highlighting. Ooh. And then on the other side, we're going to use write it in assembly code. This part is untranslatable into assembly code. Well, it is translatable, but it translates to something like this. So I will start with node value :0, because the member value is at offset 0 from a struct node. That's what this means. Okay. Now, whether you want to use these labels, is up to you. But if I were writing this program, I would be using the labels. Node underscore L is node underscore value 1 plus. What that means is it's saying member L of a struct node is 1 byte after the offset of the member value, which makes sense, right? Because value only takes up 1 byte. So this is where we're going to find member L inside the struct node. Node underscore R, you guys probably know what that is going to be defined to, is 1 byte after the member L. Now, whether you want to do this or not, it's up to you. And I also want to know the size of a struct node. So that would be node underscore R 1 plus, because R is the last member of a struct node, and it itself has a size of 1. So if I add 1 to the offset to member R, then I know the size of the entire node. Is that okay? All right? So that's how we define the structure in assembly code. Then you might say, oh, but these are just labels. I mean, these are not really structures. You're absolutely right. We do not have a construct to represent structures. We can only use labels to help us to represent a structure like this. So now we move on to this chunk of code, which is already done. So I'm not going to replicate this part here. I will definitely not give you the code of this part. But I will give you the code for this part. All right, so we get the main. So now we say main colon, and then the usual stuff that we need to do, which is to initialize the stack pointer to 0. And then we have to allocate for the local variables. So for this particular purpose, I'm going to say the stack pointer is going to point to local variable p, because we are allocating for x first. So x is going to be at 1 byte past where the stack pointer is pointing to. So the x and the p in assembly code is telling me how far away is p or x away from where the stack pointer is pointing to. Yep?
Is there a difference when we initialize x or p? Why would you just...
If you use a label, then it wouldn't make any difference. So I'm going to show you why it wouldn't make any difference in this case when we get to the code. Okay, so now we need to allocate the space. Defining the labels on line 7 and 8 does not do a single thing to the stack pointer. All that is doing is to say, every time we see x, it means the same thing as 1. Every time we see p, it means the same thing as 0. So it's not really doing a single thing about the stack pointer. So we need to decrement the stack pointer a few times, or just subtract a constant from it. So we say LDIA, x has a size of 5 bytes, p has a size of 1 byte, 5 plus 1 is 6, and then we subtract that much from the stack pointer. So we are now allocating for all the local variables. Is that okay? Are we still doing okay? Good? Okay. So now we have all the stack stuff set up in kind of, we're combining line 34 and line 35 with these few lines of code. We're allocating the space on the stack. So now we are finally getting to line 37. So on line 37, the first thing we need to know is the right-hand side, which is where is x? Well, the way we compute x is going to be LDI AX, which is the offset, and then we say add AD, because everything is relative to the stack pointer. It doesn't help you if you just know the offset. You have to add the current value of the stack pointer. Yes?
Why use LDID 0 instead of just sub D?
Because this one is more obvious of what it's doing. Subdd does exactly the same thing, well, with one minor difference, but it does most of the same thing and it saves 1 byte. So it's nicer to use subdd, but this one is more obvious of what we're actually doing. So we have add AD to get to, so A is now the address of X. Do we need to dereference here? In other words, if you look at line 37, does it look like we need to dereference the address of X? The answer is no. Yes?
So on line 14, there is something we put,
On which line again?
line 14.
Line 14, uh-huh.
Wasn't the 7 number offset from the address of x now? Then we only add 1.
What? Okay, so we subtract 6 from basically 0. So we reserve 6 bytes on the stack. Okay, and so those 6 bytes are combining both local variables. So x and p both will take up 6 bytes. So all those bytes are now allocated, and the stack pointer is pointing to the lowest byte of those 6, right? So however I want to allocate it, I'm just saying, okay, just add. This is basically d plus x. Okay, that is the address of x, which is a local variable. Huh?
D plus 1 actually, right? D plus 1 because A is 1.
D plus whatever x is, and I mentioned x is 1. Yep. So it's the address of x, and the answer is no, we do not need to dereference. Because if we dereference at this point, we'll be getting to the first byte of the array, not the address of the array. So this is the confusing part, because in C and C++, you can actually take the address of x here, and it will still compile. Because when you refer to an array, you can only refer to an array by reference. There's no way to refer to an array by value in C and C++. So that's kind of like a little trick you have to remember from your cisp310 class. So this is the right-hand side. Now we need to work with the left-hand side. The left-hand side says, we need to get to P, or at least get to the address of P first. Exactly the same kind of code. We will use a different register. So now B is the address of P. But since we're going to change local variable P, we need a dereference. But we don't need a LD to dereference. We need a store to dereference. So we store to whatever B is pointing to, and A already has the right-hand side. So this completes P equals X in the C code. Are we doing okay so far with this? Okay. So now we are ready to get to line 38. Okay, we're going to set up the call. The call says we need to get the address of P. Well, we know how to do that. Now, if you want to save yourself some trouble and say, oh, but B is still the address of P, yep, you can just push B at this point. It serves that purpose. Okay, so we can now say just decrement D, reserve a byte on the stack, store to whatever D is pointing to, register B, because B is still the address of P. I did not change B. I changed what it points to, but I did not change the register itself. Is that okay? All right, cool. And then we are now ready to push the address of N1. Now, N1 is a little bit special because N1 is not a local variable. What is N1? Let me flip back to the C code here. So if I flip back to the C code, what is N1? What kind of a variable is it? Is it a local variable or is it a global variable? It's a global variable. It is defined outside of the context of any function. Okay. As global variables, the address of N1 in the form that we define it in our assembly code. Okay, where's my? Let's just assign on. There we go. Okay, so in the form that we define it, N1, the label itself, is already the address of the structure. So that means in assembly code, okay, let me switch back to the assembly code here. All we need to do is to do a LDI, okay, wait, which one are we passing? N1, okay. So we're doing LDI A and then N1. Uppercase or lowercase doesn't really matter. Everything gets converted into uppercase before it gets processed. And that's all we need to push. So decrement D again, store to where D points to, register A. So push the address of N1, in this case, on the stack. And then after that, we just need to get the return address, which is 16 plus, and then decrement D, and then we have a stda, and then we have a jmpi to traverse. Now remember, in this program, you have to use the exact name traverse because that's how I'm going to grade your program. Is I'm going to copy and paste your traverse into a test environment that I have to see whether your traverse works. Okay? So you have to use the same name as traverse. And when it does return, I have two things on the stack. So I'm going to increment D to deallocate the two arguments on the stack. And then I'm going to LDIA with 6 again, and add that to the stack pointer. And now we're done. So line 32 and line 33 of the assembly code is only here to balance the stack. So by the time I get to the hold instruction, the stack pointer should be back to 0. Okay, which is always a good thing to have, is to make sure that your stack is always balanced. So do we have any questions about this code? Yep.
So when creating those labels for the structures outside of the subroutines,
Mm-hmm.
is that convention for whenever you create global variables?
That's how you make quote-unquote global variables in assembly code, regardless of which architecture.
Okay, say you're creating structs inside a subroutine. Would you still store that on the stack, or would you make
No. So if you're creating so it depends on what what kind of a structure you're creating. So are you talking about a local variable, or are you talking about a static local variable, or what kind of a local variable are we dealing with?
just a variable?
So a structure as a local variable inside the subroutine,
Yes.
and you want to initialize it using the equals to and then the curly brace.
Yes.
So that gets a little bit tricky, because what happens is the constants, that stuff is actually compiled with the code itself. And then what the compiler would do is it will generate the code to block copy a chunk of code that is actually attached to your subroutine to the space on the stack that it has allocated. So there are three parts to that story, okay? One is the variable is still a local variable. It is still allocated on the stack at runtime. First part. Second part, the initialization, the code the stuff that you put within the curly braces for initializing that thing, that stuff is not runtime dependent. It's compile time known. So that stuff is compiled into a little chunk of, block of code, but it's associated with a code. Okay? There's only one copy of that, and it's associated with the code. Okay? And the third part is the runtime behavior. So when you get into the subroutine, what it will do is first it will allocate a space on the stack by adjusting the stack pointer. Then it's going to do a block copy, like a mem copy thing, to copy the initialization stuff in curly brace to the space that you allocate on the stack. So those are the three pieces associated with having a initialized local variable in the subroutine.
Okay, so that only applies to, so you're saying that the structure itself would be attached to the subroutine?
Or global variables, or the global variable space. Because that's all internal to the compiler. As long as the compiler itself knows where that chunk of bytes are, it's okay. So whether it puts it into the code section or the code segment of your executable, or the global initialized variable segment, is up to the compiler to decide. So, but the general idea is there's only one copy of that. But at runtime, it will allocate the space and then initialize that space, and that is only done at runtime.
I see, okay, that makes sense.
Okay. Mm-hmm. All right. So do we have any questions about this code? Any questions of, any questions about, well, how do we know this works or not? Can we check whether this stuff works or not, right? Well, let's check it. So the way we check this, okay, I'm doing you guys another favor by copying and pasting this stuff into the test code, into the main stuff, okay? And that can be done, after main, but do not do it before main, because we don't want to run this 5 as the first opcode. Okay, so that's the bottom line. Don't put this at the very beginning. So now this program would actually compile. And so we're going to take this, copy this entire thing, and switch to my assembler. Go to the source tab, delete the whole thing. And don't forget, if you want to use the trace analyzer, everything has to start, the entire program has to be preceded by a no op instruction. That was due to a bug of Logisim, so you have to do it this way, otherwise the logic, the trace analyzer won't work. So now we paste the entire program in and make sure that we don't have any unresolved references to labels. Okay, everything looks good except for this one, because we don't have traverse defined. Okay, fine. We'll go ahead and define traverse. So I can define traverse down here. I don't really want to do anything in traverse other than being able to look at what is on the stack, right? But we can examine the trace analyzer and find out what is on the stack. So there's really nothing to do. Okay, I'll put a no op instruction here just for kakas. And then we can return right away. So we have a LD B from wherever D points to, increment D, and then JMPB. Okay, so I return right away. I'm not doing a single thing. I'm not destroying anything either. I'm just going like, okay, there's nothing to do. Let's go back. So do it one more time. And then, okay, I'm going to have to turn off this monitor here. The monitor is doing exactly the same thing as my own laptop screen, so it's becoming kind of distracting. All right, so it's assembling just fine. Okay, good. And then we go to the RAM file tab. File, download as CSV. And we'll call this tree.csv. And then we switch back onto the command line. Because we want to run this code, so I can never really quite remember how to do this in assembly. Let's find all the commands that has Java in it. And the closest we can get is, this one works. Almost. Just have to change a few things. So the only thing I have to change is the name of the CSV. Basically, it's the compiled or assembled code. This one is tree. And when we run it, we want to generate the TSV in the same place, which is fine. So here we go. All right, it's done. And what do we do at this point? We have the TSV, and how do we know the program works or not? Yep, put it into the trace analyzer, which I'm going to open here. So if you have not used this approach of doing things, you might want to consider doing it now, because I think it's really going to be helpful. Okay, so we go to the one cell in the sheet, in sheet 1, and then we go to File, click on Import, go to Upload, and then select tree.tsv or log.tsv right here. Click Open. And then the option you select in the next screen these options are important. So we have to replace the current sheet. Do not replace the entire spreadsheet. Just replace the current sheet. And the separator is tab. And do not convert text to numbers, dates, and formulae. So click Import. And this is the raw data that is coming back from the TSV, the tab separated file. And this part here, takes a little bit of time, is the execution of your program. So now we look at this thing here and go like, well, but how do we know whether the program works correctly or not? It's just a whole bunch of numbers. Well, that's not exactly just a whole bunch of numbers. Because what we want to know is what did we push on the stack? What is supposed to be on the stack? So the first thing you need to do is to have a picture of what is supposed to be on the stack. We start at location 255. That's the first byte that is useful. Where is local variable x? Remember what we did to the stack pointer? We decrease it by 6, and then x is 1 byte off from it, right? So location 255, 254, 253, 252, and 251 are the bytes in local variable x. In other words, x starts at location 251. Is that okay? What is below x? What has an offset of 0 from where the stack pointer points to? P, local variable p. So local variable p is at location 250. Is that okay? Now, what about N1, N2, and that sort of stuff? Well, the assembler can tell us that. I mean, N1 is easy to find. So what we do is we go back to the Assemble tab, and we just scroll to the definition of N1 itself. So according to this, N1 is at location 1F. Because column W is telling us the address. So at address 1F, we have the content of 05. At address 20, we have the content of 22, which so happens to be the address of N2. Is that okay? So once we know this, we kind of know, by the time we get into the subroutine, how the stack is supposed to be set up. Is that okay? So now what we do is we look into the subroutine, because we can skip a whole bunch of stuff and just go straight into the subroutine. So we want to know where is traverse. So traverse is at location 2E. So we want to look up the column correspond in the trace analyzer that corresponds to the program counter and look for 2E, because all the stuff before is not really that important. Okay? We want to get to 2E, and then we go back a little bit to find out what is on the stack at that point. Okay? So now we go back to the trace analyzer, and we focus on execute at, which is column O, and we try to locate what, 2F? Was it 2F? 2E, thank you. Okay, so we want to find 2E in this column, and I think you can actually go to search. I think that's a find feature here, and 2E is what we're looking at. So 2E, and let's see. Okay, find. Apparently it's found. There we go, cool. So you can use a spreadsheet to help you quickly go to the section of code that you are interested in, okay? So at this point, this is the entry point. This is the execution of the no-op at the entry point of the traverse subroutine. But what we are interested in is what parameter is being passed here. So remind me again, where are those parameters? Are they in registers or are they in memory? They're on the stack, okay? So if they're on the stack, we know that the RAM write operations would relate to that, right? So we have one RAM write, instruction or event here, writing to location F7, and the content that we wrote into that location was 19. That was the last thing that we put into the stack. What is that supposed to be? When you are calling a subroutine, what is the last thing that the caller would put onto the stack? It's the return address, right? Now, if I just say that 19 is the return address, would you buy that? No, don't buy it, right? You have to check that, right? Because you have to check it. Okay, I'll explain why you have to check it. So we want to kind of go back into location 19 in the Assemble tab. So location 19 is right here. Does that look like where we want the subroutine to return to? Yeah, it's right after the JMPI instruction. That's where we want the subroutine to return to. But why do you think I want you to know how to check this? And why I emphasize do not assume that is actually the return address. Because if you forget to push the return address, then you will know. If you check the trace, you will say, hey, that last thing that I pushed on the stack is supposed to be the return address. Why is it not? Oh, I forgot. Okay? Because if you don't push the return address on the stack correctly, then the subroutine will use whatever is at that location as if it is the return address and continue execution based on that. So that's why when you check the trace of the execution of your code, it is important not to make assumptions and just check it. Okay? All right. So now that we know the last thing pushed was the return address, we can now go back in time and say, what else did we push? Okay, this is the other thing that we push on the stack. What is that corresponding to? It's not the return address, it is the one thing that we pushed before the return address was pushed. What is that supposed to be? Which parameter? Because we got two parameters, right? Parameter 1, and that would be the structure pointer, right? It points to a structure. So now we ask, is that the address of node 1 or n1? I don't know. I mean, we have to check. So we go back to the assemble tab, and then we check out n1. And n1 does have the address of 1f. Whew. Okay, that's good. Is that okay? But we are also supposed to have two arguments, right? Argument 2 is supposed to be pushed before this one. So now we go back to the trace analyzer again and locate the other write operation, which is FA, okay? So now the question is, what is that supposed to be? Oh, it is supposed to be the address of P, right? Did you guys remember where P was supposed to be? It's supposed to be at location 250, okay? So you look at FA in hexadecimal and you ask, well, is that 250? And the answer is yes, because 255 is FF, right? And the difference between an F and an A is 5. So 255 minus 5 is, in fact, 250. So we did, in fact, push the address of P on the stack, not the value of P on the stack. Oh, by the way, what is the value of P? What is it supposed to be? Okay, let's check out the C code because you guys might, because there are a lot of moving points here. It's supposed to be the address of X, right? And what is the address of X in assembly code? 255, 254, 253, 252, 251, right? So 251 is the address of X. So 251 should be in the location of 250 if I initialize everything correctly. Is that okay? So how do we know? How do we use the trace analyzer and check that? Search for write operations to FA. Okay? So now we check. We go back in again, and we keep looking until we see, okay, FA got, at location FA, which is 250, is the value of FB, which is 251. Would that be correct? Did we initialize local variable P correctly? Yes, we did. 5B is 251, which is the address of local variable X, which is the entire array. And FA is the address of P. So P got initialized to the beginning of the array. So we did get all that stuff initialized correctly, and we were able to verify that by looking into the trace analyzer. Yes, go ahead. Right. And the best thing about the trace analyzer is, if you feel that this document is particularly helpful, you can just make a copy of this, right? I mean, you can just make a copy. And then the other thing that's nice about this is you can mechanically search for things. If you suspect something should have happened to a certain location, you look for it, right? So what you can do, to look for things, I think you can highlight a column to focus the search. Then you can look for things, based on edit, find, and replace. Where is that? oh, right here, Control H. And you can look for star, whatever F location that you're looking for. So FA equals 2. So that will help you locate it. So you have a lot of really kind of useful tools within a spreadsheet to help you. Now, I understand this trace is not short, okay? It's kind of a long trace, even though we did not have any actual subroutine written. Okay, let me just kind of go to the end here, just to show you how long it is. So without a subroutine, it's already using 131 rows. So with your subroutine, actually running, it's going to take up a lot of rows. So that's why you don't want to really watch the rows, row by row by row. Instead, you focus on these columns here: column M, N, O, and occasionally P. Now, P is really significant in the sense of every change to register D, or the stack pointer, is recorded. So if you just look for D equals 2 in column P, you will find all the places where you made changes to the stack pointer, which can be important because if you forget to balance the stack or you forget to do something on the stack and it's causing the program not to work correctly, you can spot that stuff. So just using this, can we check that the stack pointer is in fact balanced? Well, let's see. The last change to the stack pointer is we store a 0 into it. So it would seem to me that the stack was indeed balanced. This is why the trace analyzer is helpful. Just imagine life without the trace analyzer. What happens if I replace the trace analyzer with 1 or 2 LEDs? Then you got my previous job. I wrote firmware with only 2 LEDs. And that's without that's without the certainty of RAM is actually, the rest of the hardware stuff is actually working. So what happens in my previous job is the hardware engineers, the people who design PCBs or printed circuit boards, would do their job, design something, put in the power equations and whatnot, and then they will have the whole thing, the prototype, they call it the prototype, done, and then they would drop it on my lap and say, "Tech, make it work," assuming that they got the job done right. And sometimes they do not. In other words, the hardware itself, the circuit board itself, would not be designed correctly. So if the circuit board is not designed correctly, there's no way the software can work, right? There's no access to RAM, or there's a bus fight somewhere. So I actually had to read power equations to make sure that that part is working, because there were many times in software things should be working, but it's not working. And I hand it back to the hardware people, and then they come back to me and go like, no, it's your problem. So I learned how to read schematics and also power equations, just so that I can find out, okay, is it a software issue or is it a hardware issue? That's kind of the background of the way I teach this class too. So do we have any questions about anything that we talked about today? The main program, I'm going to save this program and make it available, because I think it's okay. I mean, this seems to be not this one. You got that one already. But this one. So do we have any questions about this code, this particular assembly code, which has just the stub of traverse, but has everything else set up? No questions of how it is set up? How about the concepts involved? Nope, it's all good? All right, so if that is the case, I'm going to save it first. Okay. I mean, if I don't save it right now and just go like, oops, my computer just crashed, or I turned it off, are you guys going to panic? No. Where do you find it? No. Well, you can go to YouTube. There's that, okay? But it's still in my assembler. So if you go to the share drive and go to the assembler sheet right now, it's still in the assembler. You just kind of copy and paste it into your own notepad, and you're all set. Okay? But I'm going to be nice and save it. So I'm going to save it as tree.ttpasm and then post it to here. All right, so I'm going to post it. We're not quite done yet. We still got 8 minutes or so, and I always find a way to fill up the time. Okay, so give me a second here to attach this first. Okay, so this is tree.ttpasm, and I know it has to have some content here. Yep, because what I'm going to say next can be very helpful in terms of making your making your program easier to write. Okay, so attached and save. There we go. So now you guys have a good starting point. I mean, if you don't have this starting point, you can just kind of port your code to here. Just copy your traverse into this program. Then you're all set. Okay. Now, let's go back to the C code, okay? And we'll focus on the conditions of line 20 and on line 25, okay? Here's the question. If I were to comment out this condition and this condition, would that change the actual outcome of running the code? That's the question. Would this program, would this subroutine know when to stop without those two conditions? It will still stop. It's just whether you have one last level, because if okay, let's say L is null, okay, and I didn't check it, right, and I just went ahead and called. I'm passing a null pointer to the next invocation, so PTR would be null, but I still have this. So it's still checking it, but it's less efficient because now I need to have one more function call, or the overhead of one more call to stop the recursion. So in terms of the actual behavior of calling and returning, it's changing a little bit. But in terms of how it's changing what is in the array, it's not changing it. Okay, so that's one clue. Okay. Of what you can do to potentially make your program easier to write because there are less things to check and stuff. Second thing, what is this program actually doing? I mean, we can trace it step by step and whatnot, but exactly what is it doing? So to illustrate it in 5 minutes, we'll do it this way. So we're going to use one of my favorite tools, which is Zerno. And by the way, Zerno is available for Windows as well. So if you have a desktop that has a stylus or pen, you can use it on that too. Okay, so let me go back to the initialization of the nodes first. Okay, and the best way to do this, wrong window, there we go. Okay, so we have N1 pointing to N2, N3, okay. So this is how we can visualize this. We have N1, my pointer is off a little bit. I wonder why that is the case. Okay, but that's okay. N2 and N3 here, okay. And then we have N2 to point to N4. So we have N2 to point to N4, and then N3 to point to N5. And then the values are 5, 3, 10. So we have 5 here, 3. Okay. So this is one visual way to look at this. This is a binary search tree. Okay. And what the program is doing is it's doing a particular way of traversing it. It's called an in-order traversal. So it would traverse the entire left-hand side first, and then record itself, and then traverse the entire right-hand side. So the way we record the 3, then we go to N4, and then try to go to the sub nodes of N4, especially the left one. There's none here. Come back to N4, record the 4. Try to go to the right-hand side. There's nothing. Come back here. And then go back to here, and then go back to N1, record the 5. And then it would do the traversal of the right-hand side. It would go to the 10, N3, and then try to go to the left-hand side, which it has. And then we'll go to the left-hand side of the N5, which there's none. Go back to N5, record the 9. Go back to N3, record the 10. Attempt to go to the right-hand side of N3, which there's none. And then go back to N1, and that is the conclusion. Okay? So if you look at that traversal, the values that you're going to store in your array is going to be 3, 4, 5, 9, 10. So when the algorithm is completed, these are the values that you should find in local variable x of main. Creating the actual C subroutine is given to you. You are just changing that subroutine into assembly. I kind of felt that it is appropriate for this class. Now, if I were to ask you, give you, and say this is a binary tree problem and you have to deal with it, you come up with the C code also, that would not be appropriate because cisp310 being the only prerequisite of this class means that you may not have the exposure to a binary search tree. But the implementation from C into assembly is not inventing the algorithm itself. So are we good so far? So have we demystified the concept of recursion? Yes? How many people kind of have this kind of mystified view of recursion before this class? It's only natural. Because in C, in cisp310, all they told you is, you can call yourself, but when you call yourself, your parameters and your local variables are not the same, okay? That is kind of vague and kind of strange to understand, but once we understand what is going on the stack, it's like, oh, okay. Subroutine recursion is no different from calling any other subroutine. So remember that, okay? If you keep thinking this looks like a loop, you are overthinking. All right, so we're out of time. Exactly 6:50 right now. I'm gonna stop the recorder and then we'll go to the lab. Next Tuesday, yes. Oh yeah.